we're going to talk about balancing reactions. Let's look at a common reaction. H2 plus O2 yields H2O. This would seem fine, however, there's a big problem with it. What's wrong? The equation, or this reaction, is not balanced. What do we mean by this? If we look at the left and right side of the reaction, we look at 2 atoms of hydrogen on the left side and 2 atoms of hydrogen on the right side, which is fine, but there are 2 atoms of oxygen on the left side, but only 1 atom of oxygen on the right side. If we wrote our reaction like this, it would violate the conservation of mass. A conservation of mass says that mass cannot be gained or lost. If we wrote the reaction like this, we would be saying that we lost 1 atom of oxygen. That can never happen. We have to account for the oxygen. So let's see what's wrong with the reaction and how we can fix it. We're going to make a table. This table is going to have the elements that are present in the reaction. In this case, we only have hydrogen and oxygen, and we're going to have tallies of each element on the left and right side. So how many elements, hydrogens, do we have on the left side? We have an H2, which has 2 hydrogens, and on the right side, we have an H2O, which has 2 hydrogens. Okay, let's move on to oxygen. On the left side, we have O2, which has 2 oxygens, but on the right side, we have H2O, which only has 1 oxygen. The problem lies with oxygen. We can't have 2 on the left and only 1 on the right. We want to have 2 on the left and 2 on the right. If this table showed 2 hydrogens on the left, 2 hydrogens on the right, and 2 oxygens on the left, and 2 oxygens on the right, then everything would be fine. However, that's not the case right now. So we want this. How can we modify the reaction to make the table look like this? Let's clear it up. If we want to have 2 oxygens on the right side, we're going to put a 2 in front of the H2O. Now we have 2 oxygens on the right side and 2 oxygens on the left side. Everything seems good, but we've created another problem. If we look, we see we have 4 hydrogens on the right side now. We have 2 H2Os. H2O has 2 hydrogens each, so now that we have 2, we have 4 hydrogens on the right side. How are we going to fix this? Well, we're going to want 4 hydrogens on the left side, so we're going to put a 2 in front of the H2. Now we have 4 hydrogens on the left and 4 hydrogens on the right. We have 2 oxygens on the left and 2 oxygens on the right, and this equation is now balanced. Let's look at another example. Cl2O5 plus H2O yields HClO3. Anytime we want to balance a reaction, we're going to make a table. We're going to make a column of elements, a column for number on the left, and a column for number on the right. In the elements column, we're going to list all the elements present in the reaction. In this reaction, we have Cl, O, and H. From there, we're going to fill in the table to show how many of each element are on the left and how many of each element are on the right. So if we do that, we find that there are 2 Cl's on the left and 1 Cl on the right, 6 O's on the left and 3 O's on the right, 2 hydrogens on the left and 1 hydrogen on the right. As we can see, each element here is not balanced. So let's fix each element one at a time. Let's start with Cl. Cl has 2 on the left and 1 on the right. We want to make that 1 a 2. So how can we make that 1 a 2 on the right side of the equation? We're going to multiply 8ClO3 by 2. So now we have 2 Cl's on the right side. But now we have a different number of hydrogens and a different number of oxygens on the right side. So let's see how many hydrogens we now have on the right side and how many oxygens we have on the right side. We have 6 oxygens now and 2 hydrogens now. This equation is now balanced. We have 2 Cl's on the left, 2 Cl's on the right, 6 oxygens on the left, 6 oxygens on the right, 2 hydrogens on the left, and 2 hydrogens on the right. This equation is now balanced. Let's look at another example. CH3SH plus O2 yields CO2 plus SO2 plus H2O. Again, we're going to make a table. Row of elements, number on left, number on right. We have elements C, H, S, and O. And we're going to fill the table according to how many of each element are present in the current reaction. We have 1 carbon on the left, 1 carbon on the right. We have 4 hydrogens on the left and 2 hydrogens on the right. We have 1 sulfur on the left and 1 sulfur on the right. We have 2 oxygens on the left and 5 oxygens on the right. Carbon is currently balanced, so we're going to move on to hydrogen first. We have 4 hydrogens on the left and 2 hydrogens on the right. We want to make 4 hydrogens on the right. How are we going to do that on the right side? We're going to put a 2 in front of the H2O. Putting a 2 in front of the H2O now makes 4 hydrogens on the right side. But it also makes 6 hydrogens on the right side. We have 2 oxygens from the CO2, 2 oxygens from the SO2, and now 2 oxygens from the 2 H2O. Moving on to S. S is balanced. Now we're left with O. O has 2 atoms on the left side and 6 on the right side. So we have to balance the left side. We want the left side to say 6 oxygens. So how are we going to make the left side have 6 oxygens? We're going to put a 3 in front of the O2. If we put a 3 in front of the O2, we now have 6 oxygens on both sides. 6 oxygens on the left and 6 oxygens on the right. Every other element is still balanced. We still have 1 carbon on the left and 1 carbon on the right. 4 hydrogens on the left and 4 hydrogens on the right. And of course, 1 sulfur on the left and 1 sulfur on the right. So this equation is now balanced. If we're given a reaction where the same polyatomic ions appear on both sides of the equation, we can balance them in the table. Let's look at an example where we can use this. If we were given ZnOH2 plus H3PO4 yields Zn3PO42 plus H2O, we would write a table as normally, but in this table we're going to include PO4 as an element in the table. Why can we do this? Because PO4 exists on both sides of the equation. It exists on the left side in H3PO4, and it exists on the right side in Zn3PO42. I want to point out, however, that even though the polyatomic ion OH- exists on the left side, it does not exist on the right side. So we do not include that in an element on the table. We still split that up into hydrogen and oxygen. So we're going to fill in our numbers normally. There are 1 Zn on the left, 3 Zn on the right, 5 hydrogens on the left, 2 hydrogens on the right, 2 oxygens on the left, 1 oxygen on the right, 1 PO4 on the left, and 2 PO4s on the right. Let's start with balancing zinc. Zinc has 1 on the left and 3 on the right. We want 3 on the left. How are we going to make this happen? We're going to put a 3 in front of the ZnOH2. We now have 3 Zns on the left and 3 Zns on the right. However, our numbers of oxygen and hydrogen are now changing. We now have 9 hydrogens on the left side and 6 oxygens on the left side. Let's move down to PO4. If we wanted to balance PO4, we want 2 PO4 on the left side to match the 2 on the right side. How can we do that? We're going to put a 2 in front of the H3PO4. We now have 2 PO4s on the left and 2 PO4s on the right. However, again, our number of hydrogens on the left side is changing. We now have 12 hydrogens on the left side. Now let's go back up to balance hydrogen. There are 12 hydrogens on the left and 2 on the right. We want 12 hydrogens on the left and 12 hydrogens on the right. How can we make this happen? We're going to multiply H2O by 6. We now have 12 hydrogens on the left and 12 hydrogens on the right. But since we multiplied H2O by 6, we now have 6 oxygens on the right side as well. And if you look, you can see that oxygens are now balanced due to that multiplication factor of 6 on the H2O. So now we have our Zn balanced, our H balanced, our O balanced, and our PO4 is balanced. So this equation is now finally balanced.